Okay, so this is the channel capacity. This is known as the channel capacity formula for the binary symmetric channel. And essentially what it says is that if the probability of error is 0, then the channel allows you to transmit full 1000 bits per second. But if probability of error becomes greater than 0, then the rate at which you can transfer the information keeps on steadily going down. And at p equal to 0.5, it becomes 0. And actually at p equal to 1, it comes back up to full 1000 bits per second. So it's a inverted it's actually a parabolic function which is centered or symmetric at p equal to 0.5. Now, when you normalize this by n, which is the length of the transmitted code word, then you get what is known as the channel capacity bound, capital C. And essentially what this says is that the rate of our channel coding scheme cannot exceed, over BSC, it cannot exceed 1 minus HB of P. No matter what we do, we cannot get our rate to be higher than 1 minus HB of P. Basically, we cannot get our rate to be greater than this value indicated by the blue line and still maintain a probability of error which is small. So the maximum rate of information transfer for BSC is given by 1 minus HB of P, bits per bit. The reason is because over BSC, the transmitter is required to allocate HB of P bits just to overcome the effect of noise, where HB of P is just the binary entropy function of the binary symmetric channel. And we need those many bits because the size of the typical set is 2 to the power n times HB of P. And so we cannot put information in those 2 to the in those n times HB of P bits. We can put the information only in the remaining 1 minus HB of P bits, and that is the reason why the rate is bounded by this capital C. And so when P is 1%, the rate is 1 minus HB of P becomes about 0.92, which means that out of 1000 bits we can actually send, our information transfer rate can at the most be 920 bits per second. Our earlier answer of 990 bits per second was wrong. Actually, it is worse than that. It is 920 bits per second. When P becomes 10%, according to our earlier thinking, we would have said that the rate of information transfer would be 900 bits per second. But actually, it is even much worse than that. It is only 530 bits per second. But still, this 0.53 is still pretty good actually if you think about it. When 10% of your bits are getting corrupted, still you are able to transmit almost about half of the total number of bits that you are transmitting. You are able to pack information in as many as about half of those bits. Now, that is quite remarkable, because otherwise, if we do, for example, the repetition coding, then the answer we will get is much worse. And so let's take an example. We will come back to this slide. I think we have seen this slide earlier, so maybe we'll just quickly come back to it later on as a summary. But let us look at the repetition code whose error probability performance is shown over here for different rates. And I have considered the length to be an odd integer because that simplifies the majority voting decoding and the corresponding probability of error analysis. And I have taken also that P is equal to 0.1. Remember, for P equal to 0.1, the channel capacity says that we will be able to send 530 bits. Basically, the rate can be 0.53, as high as 0.53. Now let us see, suppose with repetition code, if I want to get error probability down to pretty much zero, then what will I need to make the rate? That is the question for p equal to 0.1. Now I have shown this chart for different values of rate. Obviously, as I reduce the rate, probability of error goes down. But this rate of 1/3 I won't be able to use because the probability of error is still pretty high, about 3%. So you say, okay, fine, I will reduce the rate even further. Maybe I'll go up to 0.2, but still probability of error is 1%. Over here also probability of error doesn't become zero. It looks like as if it is pretty close to zero, which it is, but it is not exactly zero. The way to do that, to see that, is to plot y-axis in the logarithmic domain. And then this is the chart that I get. It is exactly same as the previous chart, except now we are able to see how the error rate is going down in a more clearer manner. So you see that, suppose if I forget about making the probability of error 0, even if I want to make probability of error to be 10 to the power minus 15, it is not 0, it is pretty low, yes, 1 out of 10 to the power 15 bits will be in error. But even for that non-zero rate, I will need to make the rate here to be 1 over 61. For each bit that I am sending, I will need about 60 to 61, I will need about 60 additional bits. The same bit repeated 61 times, or 60 times in general, I mean roughly speaking. So you can see that the rate becomes so small, 1 over 61. What was P value? P is 10%. What does the channel capacity say? How much rate we can send? It is 0.53. So you can see why repetition code, although it is a pretty nice code to start understanding the channel coding theory, why it is pretty weak actually. Because compared to what the channel capacity says that you should be able to achieve, the repetition code is highly inefficient. It reduces the bit error rate, but by doing that it ends up really sacrificing on the rate a lot. And so the advanced coding schemes that we have studied, the LDPC code, or we briefly mentioned turbo code, they try to bring this blue line kind of pretty close to this red line. Even the convolution code that you are studying right now and implementing as a part of your project will be far better than the repetition code. It will get you 10 to the power minus 15 error probability with a rate which is much better than 1 over 61. That is the entire promise of error correction coding. And specifically the channel capacity tells you that unlike what the repetition coding can give you, which is at the rate 1 over 61, your probability of bit error is 10 to the power minus 15. What the channel capacity theorem says that that rate equal C equal to 1 minus HB of P, at that rate the probability of error is not 10 to the power minus 15. It's not even 10 to the power minus 100 or 10 to the power minus 1000. At the rate of 0.53, you can get probability of error as small as you desire. You don't have to make rate approach 0, unlike what the repetition coding would do to you. And that was pretty remarkable theorem, that you can get as much as close to 0.53 or 53% of the data that you are transmitting, about 53% of that can carry information. the time when this theorem was published, which was in 1948, the general belief was that if you want to reduce the probability of error, if you want to make it approach zero, then you will have to make R, the rate, also approach zero, because in those days the repetition coding was the only technique that was being considered. But what this channel capacity theorem showed, that no, repetition coding is actually pretty inefficient. You can come up with some smart coding techniques. And the initial example was Hamming code. And then after Hamming code came Golay code. And then came that BCH code that we have briefly mentioned, Reed-Solomon code. Each of these coding techniques was more refined and more clever and more powerful than the previous technique. Then came convolution codes. That was also that is also a very powerful technique. The entire focus was on achieving this capacity bound, which is for the binary symmetric channel, it is 1 minus HB of P. And so that is where this topic of channel coding we are concluding. The last remark that I would make is that this channel capacity bound C is equal to 1 minus HB of P holds for binary symmetric channel. By a similar argument, which we are not going to cover in CT 111, the argument is similar. It is you by spending a little more effort, you can understand that argument. It was shown in the same journal paper that the channel capacity bound for the real world channels, where the actual noise is Gaussian noise, most likely, and the actual signals are voltage signals, not just bits. So in those real world channels, the channel capacity bound C is equal to bandwidth W times logarithm base 2 of 1 plus SNR. That formula is the one that we had started out with at the start of the semester. You even did one lab on that. And that time we had said that that formula forms the basis of today's communication systems and even tomorrow's communication systems, even 5G, 6G, all the communication systems today's and tomorrow's and even in the past, they are all bound by this channel capacity theorem, which is kind of the pinnacle of the entire communication theory mathematics. Okay, so with this we have concluded the topic of channel coding, and then we will start working on the final topic of modulation, starting from the next set of video lectures.